Today we're going to start discussing propagation. This is one of the more technical and mathematical topics that we have, and as you'll see in the next lecture, we'll talk a lot about probability and statistics. However, in this lecture, we're going to talk more about the general ideas and models that we have to discuss propagation and probability. It's important to get the high-level understanding of what's going on here, because that'll be crucial in understanding the more mathematical concepts later. Also, when you're looking to apply this knowledge about propagation, having this higher level understanding is going to be very critical. So let's talk about the general idea to start. Network structure and propagation is talking about how things spread through networks according to the structure of that network. Those things could be diseases, fads, rumors, viral social media content like memes or videos, and they spread the same way in networks regardless of what they are. So sometimes we want things to spread. If we're doing a viral marketing campaign, we really want to see that spread. But if a disease is spreading, we want to know how that happens so we can stop it. There's been a lot of work in understanding disease models and how they spread through social networks, because obviously a lot of people in many fields are interested in how that happens so they can prevent the spread of disease. So the questions that we're going to look at is, how does this relate to network structure? So we've been studying all of these different models of betweenness centrality, closeness centrality, eigenvector centrality, different types of tie strength and trust. How do those things we know about structure affect and relate to the way things propagate through a network? And how can we spread things better, like information, or prevent their spread, like viruses, by understanding the structure of the network and its relationship to propagation? So in this lecture, we're going to review some existing models and data. When we do this lecture in person, it's pretty interactive. So I'm going to have you taking a lot of notes and participating on the discussion boards in order to simulate some of that. But it's important for these exercises that you really do them on your own, because it will help you start to get an insight about how some of this works. However, we're going to start with a model that I've put together for you, and this is taken from a network science lecture by Laszlo Barabasi. What we're looking at here is how a link spreads through a discussion board when it's shared with different initial users. So the people running this experiment had a link that they wanted to pass on to other people, and they choose to spread this by looking either at 500 randomly chosen users, giving them the link and asking them to share it, or picking the 500 most active users on the discussion board, same number of people, and giving them the link and asking them to share it. What we're going to look at here is an 8-day simulation of what happens and how that link spreads. So we're going to start by looking at this box with the 500 randomly chosen users. And essentially you can consider each pixel on this screen to be a person. And you can see that there are some pixels already filled in. These are our 500 randomly chosen users. And don't worry too much about what placement means in here, the XY axis. Just consider each one a person, and the people that are close to you will actually be physically close. So if I spread to people next to me, it will spread out in the space near me. So let's watch the simulation. You'll see the days tick up at the bottom. And what we can see as this continues is that we see a lot of darkening and spreading of the space around where those initial nodes started. So by the time we get to day 6, we can see a really strong difference in how the network looks. There's a lot more color. We can see some really big clusters where the link has spread to. So each of these colored spots is now indicating someone who has seen the link. When we start with the 500 most active users, we get a very different picture. So you can already see that we're a little bit more spread out. And if we run this, there's a dramatic difference. The first few days, we're more spread out, but we're seeing similar effects. But by the time we get to day 5 through 8, we start to see a massive difference in what this network looks like. So we started off with 500 users in both cases. We gave them the same instructions to spread this link, but look at the difference in where the link reached. By hitting these most active users, and these are essentially the hubs in the network, it allows the information to spread much more widely, because those most active users have more connections and they're reaching out to more people. A way that we can model this on a slightly closer level is by looking at something called the firefighter problem. And this is a problem that's commonly studied in the space of looking at how things spread through networks based on the structure. So here we have a really simple network. It's just going to be set up as a grid. Each intersection point on the grid is going to represent a node. So basically each person will have a degree of 4. It'll be connected to the people above and below it in the grid and to the left and right of it in the grid. We're going to have a fire that starts at one point, and so we place that fire. And then one firefighter can be deployed to protect a point at each time step. So basically we're taking turns. So we can put down a firefighter, and then in the next turn the fire spreads to all unprotected adjacent vertices in the network. So if the fire's at one point, it'll spread to all 4 of its neighbors unless those are protected. And then we repeat this. We can place a second firefighter, and then the fire spreads. We can place a third firefighter, and so on. So let me show you an example of this. Here we have a network where I have the fire started in the middle, and now we can take a turn and place a firefighter. So I'm going to put him here. In the next step, that fire will spread to the adjacent vertices, which are here. So notice that we've gone from having the fire in one place, and now it's spread above, below, and to the right. So now we have the fire in 4 places. Now we're allowed to place another firefighter. So we put him, say, here, and then the fire is going to spread. Now it will spread from every one of these fire points. So it'll spread from here to the adjacent neighbors, and from here, and from here. So now we have a much bigger fire on our hands. We can place another firefighter, and then this repeats either until we've contained the fire or until it's filled up the entire network. So you can try this on your own, but what you should think about are some of these firefighter problem strategies. So we could repeat this example exercise I just did, but you could place the firefighters in different spots. And the question when you're doing this is to see how much of the network can you protect. Essentially we have a simplified network, but if you think of this in the context of a disease spreading, you can think of the firefighters as basically immunization. So we give someone an immunization, or we quarantine them and take them out of the network, and that prevents the disease from reaching them. And then we want to see how many people can we protect from receiving that disease. So think about this, and I'd suggest you take the slides and go through them and see what you can do to stop the fire from spreading. You can also change some of the parameters. So you could have the fire only spread to 1 or 2 adjacent vertices, or you may allow yourself to place 2 firefighters instead of 1. And we'll talk about that when we get into some more complex models going forward. So this is a really simple model. I want to now talk about some more advanced ones. Particularly, we're going to start with some disease models. So these are models that the epidemiological community has put together to study the way diseases spread. And the models are named very simply. We have 4 characteristics that we're looking at, 4 states. State S means someone is susceptible. It means they don't have the disease, but they can become infected by it. State I means that they're infectious, which means they've been infected and they can spread the disease to someone else. State R means that they're recovered or removed. So they've got the disease, they've recovered from it, or potentially they've died, but they can't spread it to anyone anymore. And a lot of our models just deal with these 4 letters, S, I, and R. But sometimes we'll introduce this other variable, E. E means that people have been exposed to the disease, but they're not yet infectious. So sometimes a disease will have an incubation period. Now we're generally going to leave that out of what we're looking at here because it's hard to think of real diseases that fit that without getting into a lot of biology that's not relevant to this class or lecture. And like I said, most of the models we look at deal with these first 3 states, being susceptible, infectious, or recovered. So let's talk about some of those particular disease models and what they mean. So we can have an SI model. That means we have the susceptible state and the infectious or infected state. This means a person's susceptible, and once they catch the disease, they remain infectious for the rest of their life. So examples of this are things like HIV and herpes. Most people are susceptible to the disease, and then once they get it, they can spread it to other people, and there's no cure to get it better. An SIR model means that you're susceptible and then you get infected. You can spread the disease for a while, but once you're recovered, you can't catch the disease again. So you're never susceptible after that. This could be things like mono or chickenpox. You get those diseases once, and then once you get better, you can't catch them again, and you can't spread them anymore. We have models like SIRS and SIS. So both of these you start off susceptible, and then you become infected. In the SIRS model, you recover, but then you're susceptible again. So this is basically a person who's susceptible, gets sick, gets better. Maybe they have a period where they're better and can't catch the disease again. Maybe not. That's what the R indicates. And then eventually they become susceptible to catching the infection again. So you can think of this like strep throat. That's a disease where you're susceptible, you can catch it, you do get better, but then you can catch it again, and in fact you can get it over and over again. A lot of bacterial infections are like this. And then just to show you how the E would work, an E model usually gets put in after the S. So you're susceptible, and then you get infected, so you're exposed to the disease, but you haven't become infectious yet. Then you proceed to the I stage where you're infectious and you can pass the disease to other people. And then in the SEIR model, you can recover, but we could put whatever we want after this. So we could have an SEIRS, an SEIS. So essentially these four states get combined together, and they give us ways that we can represent the states that a person goes through to pass or have a disease. Now, this is really good for tracking diseases, but I'd like you to think about how diseases can track or model information. Because the same models that describe disease spread describe the spread of rumors or fads, links, etc. So, let's have some discussions about this. Things I want you to think about. How do the S/I/R models apply here? If we're talking about the spread of information, what does it mean to be susceptible? What does it mean to be infectious? And what does it mean to be recovered? And if you want, you can throw in the E state of exposed but not infectious. What does that mean? So if we were to say have an SIRS model, when we're talking about the spread of, say, fads or viral videos, what does that mean? So I'm going to put up a discussion board topic. I'm going to start with a couple questions and thoughts for you, and then I'd like you to share some of your thoughts on that as well. With that, I want us to move on to one more type of model that's used in the epidemiological community. And this is the K-threshold model. The K-threshold model sounds kind of fancy, but the K is basically a variable. So we can replace that with a number. And basically, the K-threshold model says that a disease can be transmitted if at least K adjacent nodes are infected. So if we have a 1 threshold, K equals 1, that means a node can be infected if at least one of its neighbors is infectious. So in this simple network that I'm showing you here, we have nodes A and B pointing to C. When can C become infected? In a 1 threshold model, it can become infected if either A or B or both of those neighbors are infected and can pass the disease. If we have a 2 threshold model, we look at that same network. C can only become infected if both neighbors, 2 neighbors A and B, are infected. So in that case, we have to have them both infected for C to catch the disease. So again, I want you to think about how this applies to information. So if we have a 2 threshold model, what does that mean if we're talking about the spread of a video? What does it mean that we have 2 infected neighbors and that is required for us to become infected ourselves? And how can you use this to build strategies? So I have some initial thoughts for you on this. Again, I'm going to put those on the same discussion board topic, but I'd like you to take a couple notes to yourself and spend some time thinking about this. What does it mean to have this disease model applying to, say, the spread of a meme or a viral video? Okay, so let's look at how we can apply these models, the SIR models with the K thresholds, to just look at how things spread through a network. All right, so in this network we have node K and node F are infected, and they're indicated like that because they're black. Now we want to see how quickly a disease will spread through the network, and we do that by counting time steps, just like in the firefighter problem. So let's look at this network and just say we have a simple SI model. And we have a 1 threshold, which means as long as one neighbor is infected, its adjacent nodes can become infected. Okay, so in that case, on the first round, F is going to infect all of its neighbors. That includes P over here, along with Q, A, B, and O in this lower quadrant. K will also infect all of its neighbors, J, P, which already could have been infected by F, and L. Now, note that in the real world, you don't have a 100% transmission rate of a disease. So if you're near someone who's sick, you're not necessarily going to get sick, even if you're infectious. There's some probability that you'll get infected or not. In this case, we're keeping it simple, and we're just saying there's a 100% chance that if you have a sick neighbor, you're going to get infected. But in the next lecture, where we talk about probability and propagation, we'll make it more sophisticated, and we'll look at probabilities of getting infected. So after that first round, we have QA, B and O infected at the bottom, L, J, and P infected at the top. I'm not even going to bother to color code for these for you, because if we look at the second step, every node left in this cluster will be infected. They're all adjacent to P, so they'll all become infected. And the nodes that remain down here, E, D, and C, are all adjacent to one of the nodes that F infected, so they'll also become infected. So in 2 steps, this entire network becomes infected. What I'd like you to do is print this slide out for yourself, make a few copies of it, and then think about how information spreads with different models. So, for example, you could try doing this with a 2 threshold. You could also try doing it with a different model. So the SI model is the simplest. But say you made it an SIS model. What that means is that K and F would start off infected. They would spread the disease to everyone's who adjacent, same as before. F would spread it to Q, A, B, O, and P, and K would spread it to J, L, and also P. After spreading it, K and F would become uninfected and go back to the susceptible state. In the next round, we have the infected nodes, but K and F are back to susceptible. And then we look at the spread. In that case, K and F are just going to get infected again because all of their sick neighbors are going to pass the disease back to them. You can try this with an SIR model, an SIRS model, and you can even play with the number of time steps that each state exists. So for example, we may say a node is susceptible. Once it becomes infected, it stays infectious for, say, 3 rounds, and then it goes on to either the R state or the S state. If you have an R state where it's recovered and not infectious, then you could have that last for a certain number of rounds. We do it simply, just having 1 round for each thing, but you could have, say, a node being susceptible. When it becomes infected, it's infectious for 3 steps, it's recovered for 5 steps, and then it becomes susceptible again. So give this a try, because what I want you to see is as you change some of those parameters, change the threshold, change the model, the disease will spread in totally different ways. Sometimes it'll just die out. Sometimes it'll spread to 1 node and then it will just sit there and not spread to anything else. So give that a try, and I'll have you guys share some of these things on the discussion board if you're able to. Okay, so the next thing that we want to look at is an exercise that I'm going to give you that's similar, but we're going to model some of the firefighter problem in here as well. So we're going to track the way a disease spreads, but instead of each round just having the disease spread like it did on the previous slide, we're going to take turns where the disease will spread, and then you can immunize uninfected nodes, which means you essentially take them out of the network. They can't become infected. Then the disease will spread, then you can immunize another node, then the disease will spread, and so on. So it's just like the firefighter problem, but instead of working with a grid, we're going to work with a network where you have, in this case, a 1 threshold SI model. So you need one infected neighbor to get sick, every node's susceptible, and then once it gets infected, it stays infectious for the rest of the time. I'm going to give you a network on the next slide, and your goal is to see how many nodes you can immunize and how many nodes get saved. The rules are you can immunize one node at each time period. And the disease is going to start at node YY. There's a bunch of nodes in here, so you'll see where I'm talking about. And you get a bonus for protecting nodes OO and DD. They happen to be in particularly susceptible places in the network. So that's our first one. Once you get that done, you can immunize one node at each time period, and we'll have the disease start in two places, at nodes OO and NN. Or for a third scenario, you can immunize two nodes at each time period, and the disease starts at B. But I want everyone to do this first example. And when I say that you get this bonus for protecting OO and DD, you don't get that bonus if you immunize them. They need to actually have the disease stopped from ever reaching them without them being immunized. So, do this in the first scenario. Here's the network. So it's pretty big. Again, you'll want to print this out, maybe print out a couple copies. We're going to start the disease at YY, which is here. So the disease starts here. Then you can place your immunized node anywhere. So for example, say we're going to immunize node KK. I can box that off and indicate that it's immunized. And then the disease will spread from YY to all of its neighbors because it's a one threshold model. So KK is protected, but VV, WW, we have a second VV here, and D all become infected. Then we can place our next immunized node. So if I'm trying to protect OO down here, maybe LL will become immunized. It stays safe. Then the disease is going to spread from all of these neighbors of YY. So VV will spread it to G, it'll spread to H, it'll spread to 1, from both this VV and from D, it'll spread to 4, and it'll spread to JJ. So now the disease has reached a lot more of the network. So you'll repeat this process. Do it a couple times for yourself because you're going to want to try some things. And then I want you to go through and actually keep track of the nodes that you've immunized. So we know it starts at YY, and then just keep a list of each stage. First you immunize, say, KK, and your second round you immunize LL, and so on. And when you finish, I want you to take account of the number of nodes who were infected, the number of nodes that you immunized, and the number of nodes that never got infected but weren't immunized. So we'll have a total of what percentage of the node was protected. What percentage of the network was protected. Then I'm going to have you upload those scores, and there will be a separate discussion board topic for you to talk about your strategies, what nodes you chose to protect, and why. So here are some more examples. Once you've done that, if you're really into it and you want to try some other things, now assume you have a two-threshold model. Same question, how many nodes do you immunize? How many are saved without immunization? And there's a couple scenarios here. You could do one node at each time period, where the disease starts at these two places. Or you can immunize two nodes at each time period, and the disease starts at nodes OO and NN. And again, here's another example for you. Assume someone can immunize two people in each round. If you have a one-threshold model, start the disease in two places and choose them to cause the largest possible spread. So in this case, you can think of this as a disease, or you could think of it as maybe you're trying to spread a viral video. You want it to spread as widely as possible. So you can start the disease, which is your video, in two places. Choose those places so it spreads as much as possible. And then you have someone else who's trying to stop the spread of that, and they can immunize two people in each round. So essentially we're reversing the roles here. You want to maximize the spread. Same scenario here. You're trying to maximize the spread. If you have a two-threshold model, you can start the disease in two places, and you want to get it to spread as widely as possible. When you're doing this, working it out on the network, make the choices for your adversary as intelligently as possible. So don't assume you have a dumb person playing against you. Assume that you're trying to spread it, but make the choices that they would make to prevent the spread. And then finally, if that's not enough for you, repeat those exercises for different models, the SIR, the SIS, and the SIRS. All of these exercises that we've just gone through are things that I'd like you to give a shot to at one level or another so you get some practice with this, because thinking about how this works is actually really important for understanding how things spread through networks. That said, the only one that I want you to do and post to the discussion board is the first one that we discussed here, where we have a one threshold model, you can immunize one node at each time period, and the disease starts at YY. So make sure you do that one thoroughly and you keep a good set of notes of your process, report your results back, and then give these other ones a try. So that's where we're going to end for today. I'll have those discussion board topics up for you, and then the next lecture we're going to get into even more realistic models with probability included.